All right, let's get started, everyone. Just a few announcements. Make sure that you grab one of the TAs this week and demo Lab 2. The grades are in for Lab 2, but if you have a 0 in there, it just means you haven't, it means that you may not have submitted or demoed yet. But if you submitted and haven't demoed, it'll show a 0 in there until we get your demo, okay? And the late penalty is calculated based on when you submitted it. So as long as you submit it on time, you're fine, but you need to do your demo to receive your grade, okay? Also, last week we extended Lab 3 to October 27th. That's Sunday, right? So you have this week to finish that up. Is there any questions about Lab 3? Any problems? Okay. So I'll review some of that stuff since it's been 2 weeks since we met, some of the details for Lab 3. And then we have our first exam will be next week. So the way I do the exams is I give them on Dropbox. They look like the quizzes, except they have more questions, and you can only attempt them once, and there's a time limit of 75 minutes, unless you have a disability extension for that. And it just looks like the quizzes, basically. So we'll have that. You could take it anytime October 28th, which is a Monday, to the following Friday, November 1st. So you have from Monday to Friday. You could take it whenever you're ready to take it. Okay, but you only get one shot at it. Yes?
Will we still be doing class and lab like normal during that week?
Usually I just do a review that week. So I still have class, but I don't cover any new material. In the past, I've used it to do a review and then some demos. So, you know, if you feel like you're ready and you feel comfortable about the lab, then you don't need to show up. Okay? So just don't forget to take the exam next week. So the exam will cover, I have a list of topics here. We've got the RISC-V instruction set architecture. This is similar to MIPS, but there's a few differences. And by the way, the exam is open book, open notes. So we're not expecting you to memorize instruction encodings and then mnemonics and stuff like that. But we'll give you snippets of programs and ask you to find the bugs or fill in the missing instruction, or here's a line of C code, which of these assembly snippets correspond to it, or vice versa, that kind of stuff. Find the bug in the code, that kind of stuff. Topic 2 is microarchitecture, so that'll be the material that I covered up through assigning Lab 3. So this won't include the branch and jump instructions, which I'll start talking about today. This will cover the microarchitecture with the R-type, U-type, and I-type instructions. And these questions usually involve asking you to set the control signals for a given instruction, or asking you things like, if this signal is stuck at 1, what effect will that have, right? That kind of stuff, those kind of questions. And we'll also cover fixed point arithmetic, logic circuits, combinational and sequential logic circuits. Remember, sequential logic is where you have memory, where the output is a function of the inputs and the input history, whereas combinational logic is just the output is just a function of the inputs. Hardware description language with simulation, synthesis, what's the difference between those two, behavioral versus structural. And then there'll be these are just conceptual questions, and then we'll have questions on system Verilog, mostly just syntax and behavior of system Verilog. So this includes reading waveforms, modules and structure, continuous assignment, numbers, like when you have a constant value, bit manipulation, reduction operators, the always statement, sensitivity lists, which is part of the always statement, default assignments and an always statement, the case statement, sequential logic, which is clocked always statements, blocking versus non-blocking assignment, registers and RAMs, and test benches. Any questions about any of that stuff? Okay. All right, so we had the quizzes extended, I think due to the hurricane, and so they were due, I think, the 11th, and we didn't have class last week, so I didn't get a chance to talk about those. So I wanted to quickly go through the quizzes because these are very similar to the questions that will be on the exam. So in quiz 2, question 1, we had a question there. Consider the following system Verilog module. There's a module there called foo. What is a problem with this module? This question had a bug in the which answer was considered the right answer. So I set it up so you should all get credit for this, no matter how you answered this one. But if you look at the options there, we've got C is double driven. Now, is that a problem with this? Yeah, because it is double driven because you've got the assign statement is setting C and the always statement is setting C. So those are potentially in conflict. Right? So the assign statement is a circuit that's going to be, owning C, right? It's driving C, as well as the always statement. And then there's the second response there is the always block has no default assignment for C. That is, that's also a problem because in that always block, B, A, and B, that's redundant. A and B, I should say, right? A and B are two signals that will activate that always because they're the inputs. They're treated as inputs inside that always. So if the state of A or B changes, the always will trigger and set the value of C, which is the output of that always. Okay. The problem is that if B is 1 and it changes to 0, so if B changes from 1 to 0, the always statement will trigger, but it won't actually set the value of C because of that if statement, right? Because the if statement will say, it'll check, B will be false, right? And so that will actually give you an error because that always statement was set up as an always comb, right? So the compiler will detect that you have some sequential logic in there, even though your intent was to make combinational logic. On the other hand, though, if you had said always at star, which is kind of the old-fashioned way to make an always statement in Verilog, right? Always com is specific to system Verilog. But in regular Verilog, in the old school Verilog, if you did combinational logic with an always, you'd say always at star. And in that case, the compiler would not give you an error, but it would end up creating a latch there. And the latch it's a latch where B is the clock signal of the latch. Remember, a latch will pass values through when the clock is high and will not pass values through, will retain its old value if the clock is low, right? And that's basically what that's doing, is that's created a latch. Now, it's a little bit more complicated than that because you've got this A and B. You're not just saying, if you said if B, then Q gets D, that would just be a straight up latch. So you want to avoid latches. Usually if you have a latch in design, it's usually non-intentional, right? Okay, but that is also a problem. So there's two right answers to this question. But then the other ones are, I think, okay. They're not problems. So always comb and the assign statements are used in the same module. That's not a problem because that's perfectly fine. You can mix those up in the same module. If statements is used when not allowed in system Verilog. Now, an if statement is allowed in system Verilog, but only in an always block, right? So that's not a problem. There's no sensitivity list given for the always statement. Well, that's okay too because that always doesn't. That one has an implied sensitivity list because it's an always underscore com, right? And the sensitivity list is A and B. Okay. So there is a sensitivity list. It's just implied. The blocking assignment is used in an always statement. So this is a blocking assignment, the equal sign, as opposed to the less than equal, which is a non-blocking assignment. And this is fine too. In fact, if you're making combinational logic, you're supposed to use a blocking assignment statement. You don't have to, but it's a convention that's often followed. Make sense? Okay. So A and B are the correct answers, but regardless of how you answer that, you should have got credit. Consider the Verilog module shown below. How many input signals are specified? That's easy. There's one clock, reset, load, and seed. So 4. Right? This one says, assume the module is reset with a reset pulse at the start of execution. What is the value of state in the first 3 clock cycles after the reset pulse? So this is clocked logic. We have a reset that will set state to not 0, 0. So first of all, state is 3 bits, like 2 down to 0, 3 bits. If you reset it, it will reset to 1, 0, 0. And then if you're not resetting, then the state will evolve. It'll change by itself. Notice there's no other inputs here. It's just pretty much after you release the reset, it's going to go to different states by itself. So what is the sequence of states that it will follow? Well, you have to look at the logic there. So in cycle 0, we're going to reset it. So that's going to be, our reset is 1, 0, 0. In cycle 1, state 2 is going to get 0. Right? So state 2 previously would have been 1, so that's going to fall. It's going to go from 1 to 0. State 1 is also going to get a... Now this is the part that's a little confusing. So state 1 is going to get the old version of state 2. So this is one of the things that's confusing about clocked logic is that remember that the outputs of this always aren't updated until after the always finishes execution, right? What that means is that if you refer to the state variable as an input, it refers to the prior input, the old input, right? That's the input from the whatever state was in the last cycle, right? And even if I change something, like for example, see, I change state 2, I write to state 2, and then I subsequently read from state 2. But even then, because I'm using this non-blocking assignment, this line of code is referring to the old value of state 2, not the value that I just set in the previous line. You guys with me? Okay, so what that means is that state 1, the new state 1, is going to get the old state 2, which was 1, right? The most significant bit, right? And then the new state 0 is going to be a 1 if either the old state 0 or the old state 1 was 1, in which case they're both 0, so that's going to get a 0, right? State 0 will get a 0, right? So the next, what you end up with at the end of that, at the end of that cycle is 0, 1, 0. Okay? And then you do it again. So state 2 gets the old, state 2 is just going to get 0. State 1 is going to get the old state 2, which was also 0, right? So that 0 comes down to here. And then state 0 is going to get 1 or 0, which is 1, right? So that state is going to evolve from 1, 0, 0 to 0, 1, 0 to 0, 0, 1. Everyone follow that? Okay? All right. This is a very similar question. Give the value of the signal A in the first 3 cycles after reset. Now this one is actually mixing the blocking and non-blocking assignment. See that? So the first line of code is a blocking and the second one is non-blocking. So this one's going to set a new value of A by shifting it left 1 bit. And then it's going to take the result of that shift and it's going to perform an XOR with 1, 1, 1, meaning it flips all 3 bits. Right? If you perform an XOR with all 1s, it's like you're flipping the bits. Okay? All right, so the reset is 1, 0, 1. So it'll be 1, 0, 1 in the first cycle. In the second cycle, we're going to take 1, 0, 1. We're going to shift it 1 bit to the left, which will give you 0, 1, 0, right? But then we're going to immediately flip all those bits to go back to 1, 0, 1, right? So this thing actually doesn't do anything because every cycle it's going to be setting the output to 1, 0, 1. Does that make sense? And again, that's because this blocking statement is going to shift. And so this is like equivalent to taking this and substituting this in to the line below it, right? Because it's a blocking assignment statement. Okay? Okay, so that's just, yeah, 1, 0, you just get 1, 0, 1 infinitely out of that. And what's the problem with the following code? A equals A plus 1. So this won't work. This will give you an error because in combinational logic, you can't have the same variable as an output and as an input, right? Because this will create a loop, right? So this will give you an error because it was declared as always comb, and it's not written as combinational logic. Although again, if you had done this as always at star, it would allow you to do that, and it would end up creating an oscillator essentially. Although I've never tried to do that on an FPGA. I used to assign that in my VLSI design course. We used to create a ring oscillator. So you would take inverters, and you would take an odd number of inverters, although it's usually also a prime number of inverters, and you connect them in a ring, right? And then you just let it go. You power it up, and it'll actually, if you look at one of the signals that connects the output of one inverter to the input of the next, it'll look like a clock signal. It'll oscillate. And the frequency of that oscillation is a function of the technology that you designed the inverters in. So, smaller technology nodes will actually give you a faster signal out of there, right? But I've never tried that on FPGA. So always statement should be combinational but as a cycle, that's the answer. Missing sensitivity list, that's not a problem, so that's not the answer. Cannot use addition in an always com statement, that's not true, you can do that. In fact, in this class, I used to also have an example where we would do an add inside an always, and we compared that to a ripple carry adder that we designed, in low-level logic. And it turned out that the ripple carry adder was a lot slower than whatever gets generated when you just use the add, right? I don't know what kind of adder it generates for the add, right? Okay, consider the following test bench. What function does some module perform? So we've got some module is our design under test, and we're setting inputs, and then we're checking the output. And the way the code's written is if the output doesn't match something that we're looking for, we generate an error. So you can translate this into a truth table, essentially, right? So you have a truth table with, what do we have? A, B, and C. So A and B are the inputs and C is the output. How do you know that? It's not shown here. It's implied by the code. So remember that when you instance a module, you don't know what the inputs and outputs are on the line where you instance it. Like when you say some module dot ABC, I don't know. It's unclear. The only way to figure out what the inputs and outputs are to drill down inside of that some module. But if you look at the code in the test bench, it's pretty obvious that A and B are supposed to be the inputs because we're setting those and then we're checking the value of C. So if A and B are 1, we expect the output to be 1. If if A is 0 and B is 1, now notice here I don't set B, so it's retaining its old value, right? So this is 1, 1. This is 0, 1. We're expecting C to be 0. And then we have 0, 0, and it's 0. And 1, 0 is 0, right? So it looks like it's an AND gate, right? Pretty much the output is supposed to be 0, except for when A and B are both 1, right? I think. Is that right? Yeah. So if you can build a truth table from this code, and you can see that it's implying that it's supposed to be, test bench is implying that it's testing an AND gate. What are the first three values of A generated from the snippet below? This is another sequential logic, but this one includes some bit manipulation. So this one's a little, you have to, kind of write this down to figure this out. So with the reset, we've got 1 0 1 0 1 1 1 0 1 0 1 cycle 0. In cycle 1, we're going to take A0 and move that down to A4. And then we're going to take 2 copies of A1 and put that into A3 down to 2. And then the complement of A3, which is a 0, so that becomes a 1. And then A2 XOR A4. So that you're going to take A2 and A4, XOR them, that's 1 XOR 1, and you get a 0, right? So basically, you just create a table and you fill in each row by looking at the row above it, right? And and the values of the row above it. Make sense? Okay. All right, that's it for quiz 2. And then quiz 3 is about the microarchitecture. So in this one, I've got the RISC-V microarchitecture from the slides. And I realize this is a little confusing because I've got it split. I've got the design kind of in 2 pieces here, even though it's all one CPU. It's designed that way to make it, I try to make it as readable as possible. So this is this shows the control unit register file ALU. This also shows the control unit register file in ALU, but on this side we kind of have different signals. So it says, consider the RISC-V microarchitecture shown below. What are the value of reg-write WB, ALU source EX, reg-cell WB when the following instructions are in the following pipeline stages? X signifies a don't care. So now keep in mind that this is using the nomenclature that I introduced in the lecture, which is kind of non-standard. But I added, I have these signal names and I've got the suffixes after them, right? Underscore EX, underscore WB, underscore fetch. And then it's a 3-stage RISC-V pipeline, which is also kind of esoteric, right? But just keep that in mind. So we've got 3 stages, so there's 3 instructions being executed in parallel. In fetch, we have a mul H, multiply high, and decode EX, we've got an LUI, and write back, we've got an XORI. And so the question says, what's going on with reg-write in the write back stage? So we have to look at what instruction is in the write back stage, and that's an XORI. And the question is, should we be writing a register for an XORI? And the answer is yes, right? Because XORI writes a register. So that should be a 1. And then what's ALU source EX? So for that, we got to go to the EX stage. That's LUI. ALU source, what does that do? ALU source. ALU source, circled here, controls what goes in to the second operand input on the ALU, the B input. So what should that be for an LUI? Well, it's an immediate instruction, so you would expect the immediate to go in, which would set ALU source, which would require ALU source 1 to be 1. But remember that LUI doesn't actually do anything with the ALU. It's a don't care, yeah. We don't care what the ALU is doing because LUI just takes the immediate and just shoves it in a register without any kind of computing. It's kind of a copy instruction, right? So that's a don't care. And then reg select WB is referring here to XORI. Reg select is over here. Reg select controls this mux, and this mux is, you could follow the wire, this mux is controlling the input to the reg file. Which input? Well, write data, the data that you're writing to the reg file, although that isn't entirely obvious here. Because the port that this thing is connected to is not labeled here. But yeah, that's the idea there is, what am I writing back? And so you have 3 options. This is the most complex control signal because there's 3 options. We've got option 1 is GPIO in, option 2 is the immediate, option 3 is the ALU, right? So for this instruction, we should be writing back whatever's coming out of the ALU, because it's an ALU instruction, right? XOR, right? And we're in write back, reg select write back. So this instruction is in write back, and so that guy should be routing the ALU output back to the register file. You see, so these are the data paths. This is how you establish a data path. So the MUX is what's creating this data path from the ALU back to the register file. And that data path is occurring inside of one cycle. So all the data paths are from memory element to memory element, right? So we're starting from the register file, going through the ALU. Oh, I'm sorry, I take that back. We're starting from that register, right? The pipeline register, actually, right? So we're starting from the pipeline register, and we're ending with a register file. And we're going through this MUX. That's the data path for this instruction, right? Okay, here's another question. Here's another set of instructions. So we've got an add-I and fetch, a mul-H and decode EX, and an LUI and write back. So reg write back is referring here to the LUI. That should be a 1, right? Because LUI does write a register. ALU source EX refers to the mul-H, and ALU source is this guy. So what are our choices here? Choice 1 is register, choice 2 is immediate. The mul-H is not an immediate instruction, it's a register instruction, so that guy should be a 0, right? And then reg select write back refers to the LUI. So what should that be? LUI is pretty much just dumps the immediate field into a register. So for that, we need to route, let's see, what is the immediate field? First of all, instruction EX31 down to 12, right? That's the, and by the way, hopefully I don't confuse you with this. In RISC-V, there's 2 immediate fields. In MIPS, there was not. Remember, in MIPS, there was 1 immediate field. It was the upper 16 bits of the instruction. Lower 16 bits. Sorry, it was the lower 16 bits. Boy, it's been a while since I taught MIPS. But there was only 1 immediate field. In RISC-V, there's 2 immediate fields, depending on the instruction format. There's the 20-bit immediate, and there's the 12-bit immediate. There's a 12-bit immediate in R-type, right? And there's a 20-bit immediate in a U-type, right? So this is the U-type immediate we're talking about here, right? For this reg select. Make sense? There's another immediate that goes into this ALU source, instruction 31 down to 20. That's the R-type immediate. That's a small immediate. That's a big immediate here, right? You got a 12-bit immediate routed into the ALU potentially, and a 20-bit immediate routed back to the register file write port, right? So remember, there's 2 immediates. Okay, and finally one more. This one has 3 new instructions in here. Reg write back. Reg write back. So the write back is CSSRW. Uh-oh. Well, that's a problem because we don't know if that instruction is writing back. Because normally that would always write back. The real RISC-V version of that always writes to the register file. In our version for Lab 3, it only writes back if you're writing to the hex displays, right? You guys with me on that? So that instruction works differently depending on the immediate field. You can write the hex displays or you can read the switches, right? If you read the switches, you write the register file. If you write to the hex displays, you don't write the register file. So I actually don't know the answer to this one. I don't know what, I'm just going to say 1, right? Because in a real RISC processor, it would be 1, right? You guys with me? Okay, ALU source EX refers to add-I. So that should be, ALU source should be a 1, right? We're putting the sign extended immediate in, right? It's an immediate instruction. And then select write back is the CSRW. And this one, reg select probably should be a 0, right? GPION, right? Everyone see how that works? That's really all this CPU design is really doing, is taking the instruction, decoding it into these signals that establish these data paths. There's more signals than what we're asking for here, obviously, but yeah, if this is understandable, then you shouldn't have any problem with designing the CPU. Okay, how many cycles is required to perform a write to a synchronous RAM? Kind of a trick question. I mean, it's got to be at least one, right? Anytime you write to any kind of RAM, it takes at least one cycle, right? So I'm going to say 1. Okay, what is the result from performing the RISC-V mol-H instruction with input values 1111 and 0001, assuming the registers are 4 bits wide? Okay, so if they're 4 bits wide, then, and we're doing the mol-H is signed or unsigned? You guys know? Signed, right? So if it's signed, that means that the 1111 is a -1, right? Not a 15, but a -1, right? And the 1, of course, is 1. So if we multiply -1 times 1, we should get -1, right? And then that means the upper 4 bits, the mol-H gives you the upper 4 bits, right, of the product, should be what? So remember, you're taking -1 and 1, and you're multiplying them. You get -1. Now, this guy is 4 bits, so that's 1111. This guy is 0001. Okay, so the result is going to be an 8-bit. So if you multiply 2 4-bit numbers, you're going to get an 8-bit result. So you're going to have the high and the low part, right? So the answer is -1, right? So -1 is, you guys remember -1 and 8 bits? Should be all 1s, yeah. So 1111 and 1111, yeah. Right, so the mol-H is going to give you that. However, if you did the mol instead of the mol-H, then it's going to be different, because now you're going to have 15 multiplied by 1, and the result is 15, right? And in 16 bits, 15 is going to be that, right? So if you do a mol-H, the upper bits of the product will be all 1s. If you do a mol-HU, the upper bits of the product will be all 0s. That's why mol-H and mol-HU are different instructions. However, either way, amazingly, the low bits are always going to be the same. It's just the upper bits that depend on whether it's signed or unsigned. Okay, and that's it. Any questions? All right. Okay, so let's continue. Well, I'll briefly review last lecture. See, I got through all the registers and RAMs and synchronous and asynchronous. We talked about the ALU. This is the ALU code, just to show you what it's doing. Some of this stuff is a little strange, like the shifter. We had to implement that a little strangely, because for some reason we couldn't perform a signed shift, an arithmetic write shift. Why? I don't know why we couldn't do that, because it should work, but it didn't. So we implemented that at a lower level. Yeah, I don't remember what happened. I don't remember what we got when we tried that. But arithmetic shift would be greater than, right? But we just did the two greater thans because it's a logical shift. Okay, any questions about that? So you can use that code, and the problem though is that in order to implement your control unit, you're going to have this table, out a lot. It's in the lab sheet too, by the way. It's also in the slide, or you can look at the Verilog code. But you're going to have to refer to this a lot, because as you're going to have to set the ALU op for all your instructions, so you're going to have to refer to this table to do that. Yes.
Quick question.
Yeah.
Go back to that list. What's the difference between the bottom three?
They're the same. There's 16 opcodes because it's a 4-bit number, but there's only like 13 different like unique operations, and so some of them are duplicated. Some of the opcodes have duplicate functions. In the code, yeah, you can see that in the code right here. So you can see there's a duplication here and here. No, here, here, shifted. What's shifted? Oh, shifted is the arithmetic right shift, right? Arithmetic right shift. So there's 2 codes for that. And, you know, interestingly, oh yeah, and the A less than B is the default. So if you have 1, 1, 1, 1, it's going to use the default. That's that last part there. And then you can see there's a duplicate A less than B. So there's 2 opcodes that give you set less than, unsigned set less than. And there's 2 opcodes that give you arithmetic shift right. Is that right? I confirm that. Yeah, so there's the 2 opcodes for arithmetic shift right, and there's the 2 opcodes for, actually there's 3 opcodes there, right?
Yeah, you just said.
Did I get that wrong?
No, you had it right. Because you said it.
Oh, yeah, sorry. Yeah, there's the 3 opcodes, right? Bing, bing, bing. Yeah, that's it. Okay. So we have the instruction formats. Again, you're going to have this available to check while you design your CPU, because I don't even have this memorized. Then the CSSRW instruction, we talked about that. I gave you some hints on how to organize this. So we have SimTop is the test bench that you're already familiar with from Lab 2. Then we've got Top, which is what we're going to use as the top level for the FPGA. So Top has to have the pinout of the FPGA. It has to have a very specific pinout matching the pins of the FPGA, right? Clock 50 and so forth. Then the CPU goes inside of Top, and your CPU can have whatever pinout you want. That's up to you. So this part is flexible. Now, someone was asking me over email if there was any way to design a better test bench for the CPU, like test things like the reset. Like if you reset the CPU, how do you have the test bench confirm that it's resetting properly? How do you know that? The only way to do it that I know of is the CPU, because this is flexible, you can have whatever IOs you want on the CPU. You could bring the program counter out, right? So you could move the declaration for the program counter, PC_fetch. You could just move it as an output in your module line, right? You guys with me? So you just move it up from local variable to an IO variable, right? Then it'll expose the program counter here. Now, why would you want to do that? Well, because then you could create your own test bench that wraps just the CPU, right? In other words, instead of using SimTop, I mean, you can still use SimTop for your top level test, but you could create another test bench that just looks at CPU. And then you could put stuff in there and check the program counter, make sure it starts at 0. Then you might say, well, what else? I mean, not really much else you could check with the program counter, and it just resets to 0 and it just counts by 1 each cycle. Yeah, but you can take the register file write ports, the write address, the write data, and the write enable, and you can expose those to the CPU interface as well. You can bring those out. Then you can have your test bench monitor what's being written in the register file. And once you have that ability, then then you have full testing capability because you can literally watch all the writes to the register file and your test bench could confirm that every write is happening correctly. Now we don't require that in Lab 3. Probably should though. It would be a good requirement, but it's a little complicated to set up because of the lag between the program counter and when those writes have to happen. Remember, because it's a 3-stage pipeline. If you've got a register write happening at address 3, then you're going to see the PC fetch at 3, right? But you're not going to see the actual write for another 3 cycles after that, right? So you're going to have your test bench is going to have to be aware of the fact that it's a 3-stage CPU and that it should expect a 3-cycle latency between the address of the instruction and the corresponding action of that instruction in terms of what it writes. Make sense? So that's an option. But like I said, the point is that that CPU interface is up to you. Okay. Okay, then I went through all of this stuff. Is there any questions about the fetch stage? Fetch stage is pretty simple. It's pretty much just the program counter accessing the instruction memory. The only signal in the fetch stage at the moment is PC fetch. Now that's going to change for Lab 4. But right now there's only really one thing in there, right? PC fetch. You might say, what about the instruction you're fetching? Well, that comes out in the next stage, right? That's actually in the execute stage. You guys with me? Okay. Yeah, so then the decoder is in the execute stage. The register file is in the execute stage. I mean, reading the register file, I should say. Then we've got the write back stage has a number of signals. We've got reg write, reg select, whatever this is. GPIO in write back. Whatever this signal is, not labeled. This is instruction WB, I guess, right? Makes sense, right? Because you've got instruction EX coming in, so instruction WB should come out, right? And then R, what's R? Result from ALU, EX, result from ALU, write back. Does that make sense? Is that clear? So the write back stage is pretty much just all the things in EX that you have to delay to get them into the write back stage. And again, these registers are just one line of code, pretty much always at pause edge clock, output equals input. That's, you know, now you might say, wait a minute, don't you have to enable them, reset them? What about the resets? You don't have to reset them, although probably a good idea to reset the reg write, right? But I don't think anyone ever does that. The reason I say that is if you don't reset it, it may be 1, right? In which case you're going to inadvertently write to a register, potentially. But that usually doesn't cause a problem because then after that, you run your whole program. Usually doesn't cause it. I don't think it causes an issue. Should be fine. But you probably should reset it. You guys with me? What is reset, by the way? What's the purpose of reset? It's to put the system into a known state at the beginning, right? When I was in school, they called it the sanity state, right? It just puts everything into a known state. And ideally, you don't want it to be causing any damage, right? Or you don't want it to be writing unintentionally, right? So probably you should have a reset for that one. But a lot of these other registers, you don't need a reset for, okay? Also, FPGAs make it easier because when you program the FPGA, it automatically resets every register to 0. If this were an ASIC, a regular chip, and you don't have a reset, that's more of a problem because when you power it up, all the registers come up random. You guys with me? Random. Okay, so all right, so there's the whole CPU, and then I went through a bunch of examples. Anyone have any questions about these control signals? No? Okay, good. That means I'm getting better at this. This is usually confusing. Then we've got the example test program. So this is what I was talking about with the test bench, is that every one of these instructions, not all of them, but almost all of them, almost all these instructions write a register with an expected value, right? So if you exposed your register file write port to the outside world, You could design a test bench around it that would check and make sure that all these values are being written, the right values are being written to the right registers. You just have to make sure that you deal with the timing somehow, right? You don't want them. By the way, we used to have, I had a TA in this class a few years ago, and he decided that he was going to automate the grading for these labs. He was going to write his own test bench, and then you would submit your lab 3, and he'd just run his test bench, and then the test bench would tell you what grade you got, right? And he thought, well, this is exactly what System Verilog was designed for. There's no reason why we shouldn't be able to automate the grading of these labs. And it turned out to be a horrible failure because half the students got a 0, and they were really upset. And it turned out that, you know, he was just checking for these values in the wrong cycle, and he couldn't, because everyone's CPU works a little differently. They don't all have the same values in the same cycles, right? So that's the reason why we do demos now. There's no way to automate the grading of this thing. At least no way we found. Okay, so then we talked about the binary to decimal conversion. This is another one of those fixed point things. Eventually, we'll figure out how to implement divide, and we won't have to do any of this anymore. One of these days, somebody's going to figure out how to make a divide instruction. But until then, we're stuck with this fixed point multiply. So this is a modulo and divide by a constant. Can be done with fixed point. I think it always works. All right, and the problem is there's round off errors, but I think we're able to control that with using, you know, 32-bit precision gives us sufficient precision in order to avoid any wrong answers in this algorithm. So the idea is that, you know, you've got a modulo by 10, which means you just divide by you multiply by 0.1, and then you take whatever the product of that is, or you take the fractional part and you multiply the fractional part by 10. Make sense? So if you have 5, you multiply it by 0.1, you get 0.5, and then you multiply it by 10 again, you recover the 5, right? You might say, well, that's pointless. Well, yeah, but like, let's say you have 65. You take 65, you multiply it by 0.1, and you get 6.5. Then you take the 0.5 and you multiply that by 10, you get the 5 back, right? That's kind of that's the idea. And then for the divide by 10, we just, you just multiply by 0.1, and you take the integral part of the product, the non-fractional part of the product. Okay? So as far as I know, if you use 32-bit, 32 fractional bits for your 0.1, then you should be good, as long as you round that value, by the way. So the way you get the 0.1 is you take 2 to the 32nd power, and you divide that by 10, but that's a fractional number, and you have to round it up. So in hex, it's 1 followed by 6 nines followed by A. 1, yeah, that's right? Yeah, 1, 9, 9, 9, 9, 9, 9, A. That's 0.1. That's 1/10 of the way through the numbers 0 to 2 to the 32nd power minus 1, or 2 to the 32nd power. Okay, yes? Yep.
Supposed to implement without branching?
Yes. Yeah, there's no branching. Yeah, so you have to, so the way I like to do it is you can write your code in a way where you can just take like 5 instructions and copy and paste it. But you have to be careful how you do it. You have to be careful how you code it so you can facilitate that. Okay, so let's talk about branch instructions then. So this will be for lab 4. So branch instructions are built with PC relative addressing, just like they were in MIPS. But you may say, wait a second, MIPS has a 16-bit immediate, and RISC-V has a 12-bit immediate. Does that mean the branches are limited to only a 12-bit distance that they can branch? Yeah, I believe so. How many bits do we have? Let's check out the B-type instruction. So this is a new type of instruction, B-type. just for branch instructions. So this one has actually more than 12 bits of immediate, right? So it has an opcode that's 7 bits, a func3, which is 3 bits, that's 10, plus 2 registers, 5 bits each, that's 10, right? I get that right? So that's 7, 10, 15, 20. So yeah, so 20 bits, and whatever's left over from that's only 12, right? So there's 12, yeah, 12-bit immediate. Yeah. Yeah, that's that, do I have that right? Yeah. Yeah. But the problem is, this is what really stinks about RISC-V. The immediate value is kind of scrambled. So if you look at the upper, let's see, that's 1 plus 6, 7. So upper 7 bits are part of the immediate. And then you got 6 bits over here. No, not 6. 4 down to 1 is 4 plus 1, up 5. 5 bits here, 5 bits here. This always confuses me. There's 5 bits down here, and there's 7 bits. So 5 plus 7 is 12, right? Yeah, got it right. Yep. Makes sense? But look at the ordering. Immediate 12, and then immediate's 10 down to 5, concatenated. Then you've got immediate 4 down to 1, and concatenate with immediate 11. Yeah, so basically you have to reassemble the immediate field from bits that are all over the instruction word, right? So how do you do that? Well, it's really confusing, so we just give you the code for that. Now the other thing is, if you remember, before I get into that, I want to mention, remember in, I don't know if you remember this, hopefully you remember this, but in MIPS, the immediate for the branches was basically a word address, right? So to get the byte address, you had to multiply whatever was in the immediate by 4, right? In RISC-V, the branch target is actually a half word address. So it's multiplied by 2. Right? In other words, the immediate in the branch instruction is referring to a 2-byte address, a 16-bit address. Why is that? Why do they do that? I don't know exactly, but I think it's because RISC-V has a 16-bit instruction mode for compact microcontrollers that have very little memory. Does it make sense? So they got this from ARM. ARM had a thing called ARM thumb mode. ARM thumb instructions were like an 8-bit, no, 16-bit, sorry, 16-bit. ARM had a 16-bit version. I've never seen anyone use that though. I'm sure someone has, but most ARM processors are 32-bit mode, right? RISC-V, same thing, they have a 16-bit mode. So the branch instruction is a half-word address, okay? All right, so what does that mean? That means that you have to calculate, you have to reassemble the branch offset, and normally you would have to multiply it by 2 to get the byte address. But remember that our processor has a word address in the instruction memory. So your code actually has to divide the branch offset by 2. Okay, to get the word address, right? So because we don't want a byte address in our CPU, we want a word address. All right, so the way you do that is with the following code, and it's basically just bit twiddling. So the branch offset is going to be comprised of the instruction EX bit 31 concatenated with instruction EX bit 7, then concatenated with instruction EX bits 30 down to 25, concatenated with instruction EX bits 11 down to 8, right? And then an extra 0 at the end of that to multiply it by 2. Okay, so this will give you the byte address for the branch target, the not the target, but the offset, right? Why do I say offset? Because then you have to add that to the program counter. That's an offset to the current program counter, right? And then you have to also, as I mentioned, divide by 2. So notice that the branch offset EX is 12 down to 2, implying that I'm knocking off bits 1 and 0. So I'm shifting this by, so I'm basically shifting it here to the left by 1 bit, but then I shift it back to the right by 2 bits. Why am I doing this? Because I want to show you the logic, right? This is the byte offset, and then this is the word target address, right? 2 lines of code. Okay? Make sense? Now, you might have noticed something here. Notice I say PCEX. Now, I actually haven't shown PCEX anywhere yet. I've been showing PC fetch. Remember, I mentioned in the fetch stage, the only signal in there is the PC, right? PC fetch, right? But this says PCEX. What is the difference? Okay, so PC fetch is the address of the instruction being fetched. PCEX is the instruction of the address of the instruction being executed. There's a distinction here, and this is the difference between MIPS and RISC-V. So in MIPS, if you wanted to create an infinite loop where a branch instruction branches to itself infinitely, how would you do that? Well, you would just type loop, you'd type loop colon branch to loop, right? But how would that look in machine code? In machine code, it would look like this. The branch offset would be -1. Because in MIPS, the branch offset was calculated relative to the next instruction after the branch. Whatever instruction was being fetched while the branch was being executed, which would be 1 instruction down the road, right, in the instruction stream, that would be where your PC was relative to. Okay, so if you wanted to branch to yourself, your offset had to be -1, right? But in RISC-V, they changed that. I don't know why. In RISC-V, if you want to branch to yourself, the branch offset has to be 0 because the branch offset is calculated relative to the branch, not relative to the instruction that's after the branch in the code. Okay? So who cares? What's the difference? Well, what that means is that if you were following the MIPS way of doing things, you would use PC fetch when you calculate your branch target. But if you're doing the RISC-V way, you have to use not PC fetch, but PCEX, which is the delayed form of PC fetch, right? You have to delay PC fetch by 1 cycle. Does that make sense? Yeah, so see, this is foo. My target, my instruction has a label of foo, and then my target is foo. So these guys, they're creating a loop of 1 instruction here, right? But you can see the difference in the offsets. Okay? So how do you create PCEX? Because I haven't actually shown that anywhere. Well, you just add a register, delay register. Yeah, I've got it in the block diagrams. We'll get to that in a minute. Any questions about that? All right, so let's branch. Yeah, so this slide I'm trying to show how I decoded this, right? So this first table is mapping the bits from the instruction to the bits of the offset value. And this table is doing this one is doing the reverse, except the difference is, in this case, I'm sorting by instruction EX bits, and in this case, I'm sorting by the offset bits, right? So this is bits 12 down to 1, and this is 31 down to 7, right? Make sense? But it's not that, you can just use my code. These tables are meant to illustrate what my code is doing, how the bit twiddling is creating the offset. Okay, how about jump instructions? So there is a J-type, just like there was in MIPS. But this one's possibly even crazier. So if you remember from MIPS, there was the J-type instruction did not have a destination register. It just was pretty much the whole, like all 26 bits, whatever was left over after you took the opcode out was just address, right? And they used a pseudo direct address. In RISC-V, it's not a pseudo direct address. It's still a PC relative address. But again, the bits are all scrambled. Now you might say, well, why is there a destination register? What's that all about? That's for the jump and link. That's the link address, the link, and you have to implement that in lab 4 as well. So in RISC-V, all jumps are jumps and links. If you don't want to jump and link, then you just set the destination register to 0. Okay? Does that make sense? Yeah, kind of, because jumps are probably most commonly used for subroutines, right? Calling a method that you have to jump and link for, right? When would you use a jump without a link? Well, usually it's just if you can't jump far enough with a branch, because branches are limited, especially in RISC-V, right? RISC-V, there's only, remember, there's a 12-bit immediate in the B instruction, and that immediate is a 16-bit address. So in terms of instructions, it only gives you 12 to the 11th power range. And it's signed, so it's actually negative 2 to the 10th to positive 2 to the 10th minus 1, right? So with the branch instruction, you can only go 1,024 instructions back or 1,023 instructions forward. That's it. So if you got to go farther than that, then you have to combine the branch with a jump that gives you more range, right? Make sense? Okay. How much do we have here? We have a 20-bit immediate, right? Remember in MIPS we had 26 bits and a J-type. Okay, anyway, so there's the code. Same thing, I gave you the code. I tried to show these tables, but it's confusing. It's basically just the bits are kind of scrambled, right? But essentially, you're taking the bits, you're assembling them into a number, and you're adding that number to the program counter. That's essentially what you're doing here. Okay. Oh, and there's a jump register instruction as well that uses the I type. And why is that? Because that one requires a source register because we're using the source register to calculate the address we want to jump to, right? And then there's the destination register, which is used to write the link address, the return address. Okay? Make sense? Now, this one also uses the immediate, though. You might, what's the immediate field for? Because it takes the contents of RS1 register and it adds it to the sign extended immediate. So we get, this is a little bit more versatile than the MIPS version. The MIPS version, the jump and link register or jump register would just take whatever's in the register and put it right in the program counter. This one is a little bit nicer because it takes what's in the register, it adds the immediate offset, and then it puts that in the program counter. Make sense? Okay. So you have to create, a data path for this stuff, obviously. Okay, so here's how I propose to do this. This isn't the only way, but so I've given you the code for the branch address, the JAL address, jump and link address, that's the J-type calculation, and the jump and link register address. So basically there's 3 possible ways in RISC-V to calculate a target for jumping or branching to, right? In addition to the PC+1, which is just your standard control flow, right? So what I propose is that you calculate all 3 of those always, even regardless if it's a branch instruction or a jump instruction. You just always calculate those with an assignment statement, and then you feed those into a MUX along with the PC+1. So this gives you 4 options. This MUX, which I'm controlling with a signal now called PC source. PC source will have a value of 0 to 3 that will determine where you go next. 0 means go to the next instruction. 1 means that I want you to go to the branch target. 2 means I want you to go to the JAL target. And 3 means I want you to go to the jump and link register target. right? So the control unit just has to set that depending on what kind of instruction you're executing, okay? Does it make sense? But there's a really important issue that you have to resolve. And for that, okay, so the problem is that if I have a branch instruction, let's say I've got a branch instruction and it's executing, right? So when the branch instruction executes, I'm going to be calculating the target of the branch, and I'm going to be resolving the branch, right? Determining if it should be taken or not taken, right? The problem is that if it's taken, I have to update the program counter, but I can't even do that until the next cycle, right? Which means that when that branch moves from execute to write back, I'm going to be fetching the target, right? But the problem is that there's a third instruction involved here, which was the fall through. Whatever instruction was after the branch will have already been fetched, right? In other words, if I'm sitting there executing a branch, I'm also fetching the next instruction after the branch in parallel to that, right? It's going to take me a whole cycle to figure out what I want to do with the branch, and it's also going to take a whole cycle to fetch the instruction that comes after the branch, right? By the time I get done with both of those things, I now find myself in a state where I've already fetched the fall through instruction, which is what I would have went to if I didn't take the branch, but I do want to take the branch, but it's too late. I've already got the one that's going to take the branch. So to solve that problem, I have to stall the pipeline, meaning that as the fall through instruction, so it's being fetched before I even know what I'm doing with the branch, it's being fetched. The fall through, as it passes from the fetch stage into the execute stage, it's going to have to be, instead of just passing, instead of just moving from one stage to the next, it has to be converted to a stall, a zero instruction, a no-op instruction, or sometimes people call it a bubble, right? It has to be converted in that transition, right? Now this creates some issues for us though, because basically you have to just be careful that as it passes from one stage to the next, it gets converted into this no-op. Does that make sense? So how do you do that? So the control unit is going to generate a stall signal, as well as the PC source, right? It has the PC source, and it's going to put a stall signal out. Anytime the PC source isn't zero, PC source 0 means go to the next instruction. Anything other than a 0 means that you're either branching or jumping, right? So whenever the PC source coming into the control unit is not 0, that means the stall should be 1, right? But the stall signal is referring to the fetch stage. So the stall signal is going to have a suffix that's _fetch, right? Not _ex. Why? Because the target of that stall operation is whatever's being fetched, right? So most of the signals coming out of your control unit are going to have _ex in them. The stall one's going to have _fetch because it refers to the fetch, okay? Now the problem is that you would think that, okay, if you're just going to take the instruction from fetch and pass it into execute as a 0, just use a mux. It's a big deal. Just use a mux. But you can't use a mux because the instruction memory is synchronous, which means that you have to, you're going to get the next instruction no matter what. You really don't have any control over it. It's going to take one cycle to read the instruction memory. You have to connect that directly into the fetch stage, right? So the way that we've figured out how to deal with this is you fetch the instruction, the fall through instruction gets fetched, the stall signal that's generated in the execute stage will be called stall _fetch, but then it will be delayed by 1 cycle to become stall underscore EX. So basically what happens is the control unit sends a stall signal to the fetch stage, and in the next cycle, that stall signal that I sent to the fetch stage will then become stall underscore EX. In other words, the stall signal will follow the instruction into the next stage. You guys with me? Okay. So what ends up happening, and this is a little weird, the control unit has an output called stall fetch, but then it has an input called stall EX. And it's the same signal, except you might say, wait a minute, then it's a loop, then it's a combinatorial loop. You've got an output, control unit's combinational logic, you're going to have an output called stall and an input called stall. They're the same signal. You're going to end up with an oscillator. No, because you're going to break that loop with a register, right? So the control unit says stall out, then I have a stall in. The stall in is a reflection of what my stall out was in the previous cycle. In other words, so when I say stall, when the control unit says stall, it's sending a message 1 cycle into the future, basically. It's sending a stall, and then 1 cycle in the future, it will receive that stall signal. If you don't do that, then it's bad times, because model sim will lock up to the point and you can't even control C it. It's like hard lockup. Because you end up with a combinatorial loop which triggers an infinite loop of events that happen inside the simulation environment, right? And it'll just lock the simulator. So you have to make sure that you're going to create this loop, stall out, stall in, but there's got to be a register that breaks that loop so it doesn't become a combinatorial loop. Okay? You guys with me? Okay, so that's what it looks like. So I'm going to have my addresses coming out of the execute stage into this mux. And then PC fetch will get one of these execute targets after the rising edge of the clock. Likewise, I have a stall fetch that's going to come out, and it's going to get delayed 1 cycle to become stall execute, which is then going to go back into the execute stage. Okay? So in other words, this stall signal is like saying, note to self in the future, don't execute the next instruction. Ignore it, right? So then in your control unit, you will have an instruction in there, but you're also going to have a stall EX that pretty much says, don't do anything, ignore it. Take the instruction, but don't act on it. Don't set register right, don't set GPIO out, don't do anything. Okay? So that stall underscore EX will be an if statement right at the beginning of your control unit that'll say if stall underscore EX, then just set all your outputs to 0, else do everything else, right? Does it make sense? Okay, oh, and likewise, check this out, PC fetch too, PCEX, right? PCEX is the delayed version of PC fetch. This is just for calculating these target addresses. Does that make sense? Yeah, this took us a while to figure out as we developed this stuff. We tried doing this a number of different ways, and this is the best way to do it. But basically what this means is that every time you encounter a branch that's taken branches only, or jumps, you're losing a cycle because you're going to have your control unit's not going to do anything on that fall through instruction. The fall through instruction is going to be wasted. I mean, wasted. I'm talking like in terms of time, because normally your CPU will execute an instruction every cycle, except for this branch instruction, in which case you're losing a cycle. You have an instruction that's just a no-op in there, not doing anything. So the more branches you have in your code, the lower your instructions per cycle are going to be. The lower your throughput's going to be, right? Make sense? This is especially a problem, big problem, if you have a deeper CPU pipeline. This pipeline is, you only take a 1 cycle penalty if you get a branch. But if it's an Intel CPU that has 14 pipeline stages and you get a branch, that's big problems, which is why a big part of the novelty of Intel CPU technology is their branch predictor. They have a branch predictor that's very accurate at predicting branches, because if they don't predict the branch accurately, then you lose a lot of performance, right? In fact, that's kind of what made Intel the kind of king of CPUs, was their branch predictor technology. Okay, any questions? Okay, so keep in mind we've got 1 week left for Lab 3. TAs will be in the lab this week. If you have any questions, talk to them or me. Don't forget to take, we don't have any quizzes, but we'll have the exam next week. If you don't want to come to lecture next week, that's fine. It'll be optional. I'll still post it on YouTube, but I'll just be reviewing and maybe reviewing for the exam and the lab.